What's going on, guys? Welcome to LetThereBeMath again. And following from the previous video, we're now going to be looking at a very special kind of integral, which is the numerator is the derivative of the denominator. And as we discussed in the previous video, this is going to turn out to be the natural log of whatever function we have in the denominator plus the constant c. Now we should point out that because the natural log is only defined for positive values of the argument, we're going to have to take into account the fact that the function must indeed be greater than 0. So we have to choose the values of that argument which are going to be greater than 0, and we just need to specify that in our result. Now we're going to start off with the following integral. Now at first glance it doesn't look like any type of integral we have encountered so far. We can't really solve it using the techniques of the power rule or any other type. But if we notice very carefully, it looks like there's a relationship between the denominator and the numerator. Now, the first thing we should probably do in this kind of integral is we're going to grab the denominator and we're going to differentiate it. So we're going to start off by doing this. We have a plus x squared. And if we differentiate that, we get 2x. Now, if we look very closely, we look at the numerator and it's exactly 2x. So it looks like this integral is already in the form that we desire, which is the numerator is the derivative of the denominator. So now we're going to go ahead and we're going to integrate that using this general formula. And as we expect, that's just going to be the natural log of the argument at the bottom. So that's a plus x squared. And that's going to be plus the constant c. And of course, we should say that a plus x squared is going to be greater than 0. So that's the values of x for which this function is defined. Now moving on to the next example, we look at this. This looks a little bit more challenging, but we should still be able to apply the same technique that we have been using so far. So the first thing that we are going to notice here is that we have a quadratic equation or quadratic formula in the denominator, and we're going to differentiate that. We should get a linear function. And it does look like the numerator contains a linear function. Now the first thing we're going to do is let's take the denominator, we're going to differentiate that, dx x squared plus 3x minus 1. And now if we go ahead and differentiate that, we get 2x plus 3. Now at first glance, we look at the numerator, it doesn't actually look like it has the same form. However, if we're very careful with the way we define it, we look at 6 and 9, those two numbers are both multiples of 3. So if we were to rearrange this very slightly, we could perhaps get it into this form. So let's go ahead and rewrite that integral in the following way. We're going to have the integral of 3 times 2x plus 3, and then divided by the same expression in the denominator, x squared plus 3x minus 1. And now we have exactly what we wanted. So we know that there's going to be an extra factor of 3 at the front of the answer. And in fact, if we look at just this portion of the expression, this is in the exact form, numerator being the derivative of the denominator. Okay, so now we're going to just apply that. Now, a very quick thing that I like to do with integrals is whenever you have a constant floating around as a factor in your integral expression, what we can do is we can actually extract it out of the integral. So we can actually place that outside of the integral, and that makes it a little bit neater to deal with. So now we have something that looks very straightforward. So whatever value for that integral, we're just going to multiply it by 3. So let's go ahead and do that. So now we're going to take this to be 3 times the natural log of the denominator expression, x squared plus 3x minus 1. And then we're going to add the constant c. Now you might recall that since the constant should also be multiplied by that factor of 3, we should normally just write 3c, but that doesn't matter because c is an arbitrary constant. So and a constant multiplied by another constant is just going to be the same thing. So we're just going to leave it as c for the moment. And now we know, okay, the argument should be greater than 0, so we can make that restriction, or we can simply write it as the absolute value of the two sides, and that's going to make sure that this quantity remains defined. Now for the next example, we're going to look at something that looks a little bit more intimidating. So at first glance, it doesn't actually look that challenging. But here's the trick. So if you look at this integral, it doesn't actually seem like the denominator differentiates into what's in the numerator. And we can actually test that if we grab this function. We have x plus the square root of x. Now what is going to happen here is this one is going to become 1. However, this one, we know it's x to the power of half. That's going to be x to the power of half. And when we differentiate it, what we're going to do is we're going to bring the power down, which is half, and then we're going to subtract 1. And that's going to make it into the following. So it's going to be 1 plus 1 over 2. And that's going to be a minus half, so that's just going to be square root of x, like that. Now if you look at that expression alone, that doesn't look anything like what we have in the numerator here. So you might be wondering, why did I choose this example? Well, the thing is, if we actually factorize this in the right way, we can actually get it into this exact form. So what we can do instead is, we're going to factorize the denominator, and we're going to extract exactly 1 square root of x. So we're going to write it in the following way. We have a square root of x here. Now this one is just going to be square root of x multiplied by itself. And then for this one we just have this 1 multiplying that. And now we have the integral in this form. Now it's still the same function, so you might be wondering what has changed out of this expression. Well, if you look at the expression in the brackets, we can now look at it and we can try to differentiate that to see what we get. So we have root of x plus 1. Now this one, as we know, is going to become 1 over 2 root of x. And if you look at it closely, it looks like this function is in fact having this same expression in the numerator, except we have rearranged it so that it appears over here. And the only thing we're missing is that factor of 2. So what we can do to adjust that is we can simply have a 2 over here, and then we're going to place a 2 at the top, so that we now have the exact same expression that we need. And now we're going to rewrite this in the following way. So we're going to take that away. Now we have a 2, which I'm going to place at the front of the integral. And then I'm going to bring that into the numerator, so we have 1 divided by 2 root x dx, and now we have root x plus 1. So now if you look at that integral, we know, okay, now we have exactly the same thing we wanted. We have the numerator is the derivative of this denominator function. So now the answer is going to be 2 times the natural log of the square root of x plus 1 plus some constant c. And that's going to be our final answer. So even though we started out with a function that didn't actually look like it could be integrated using this method, we were able to do that simply by manipulating that expression in a clever way. And that's something that we sometimes need to do when we look at functions like this one. We have to think of creative ways to actually solve that and get it into the form we want. Now let's go with the last one. Now the last one is a very straightforward example. So it's just a binomial expression with a power of -1. But we already know this is going to take the form of a natural log, because if we look at the derivative of that denominator, 3x plus 5, that's simply going to turn into 3, which is a constant. And all we need to do to that integral is we're going to make the numerator 3 by also dividing by 3 like that. So now we have the expression, we have the natural log of that expression, and we have a factor of 1 over 3 at the front. So let's just put that over there. So we have 1 over 3 natural log of 3x plus 5 plus the constant c. And that's going to be our final answer. So hopefully this revealed a very clever way in which we can actually apply this very simple form of the integral to a variety of different examples. And in the next video, we're going to be looking at a little bit more into this application of the derivative of a function being the numerator and the function itself being the denominator. As always, if you enjoyed this video, make sure you hit the subscribe button if you would like to see more content from LetThereBeMath, and I will see you guys in the next video.